My name is Sebastian Rode. I'm founder and CTO of the Smart Robotic Systems GmbH. We have a product called Skyder, and we build automation and communication system for drones. So we believe drones are the Swiss Army knife on industrial sites, and drones can apply it in many occasions on industrial sites, for example for site security, for logistics, so transport, data acquisition, for inspection things, for time series of machines, or time series of pictures of machines, for time series of buildings, for rails, whatever. So everything where you can take a picture from and what you need to document in some way can be used, can be inspected with drones. Skyder itself is a software and hardware development kit to build a drone system. It's not a drone system. We are not selling drones. We are building, or we are creating complex drone systems for specific customers that are suited towards that specific customer. And for that, we have a software and hardware stack for communication and automation. And it's particularly important that we can really go into the company and make the drone system, make the user interface fit to what the customer actually needs. Which means we have usually on the ground something like this, which is a small embedded computer. It's not a bare metal system. I have to emphasize that because everything I'm going to be talking about today is a little bit focused on that. And we have a small device like this, which has several communication technologies on board, which is on the UAV usually, which interfaces with the UAV, and we can actually manage and control the UAV through this system. And this is the reason, basically, because we are in a somewhat critical area there. It's aerial. We have something in the air which has a certain danger for people around, and so we decided that we want to have C++ as the main language, because we have certain guarantees there that we can rely on regarding timing. We could possibly let it run on a real-time operating system and so on. So on the other hand, we have a user interface, and we want to let users control our system, and it should look nice. It should look, should be possible to operate the system, a mobile phone. It should be possible to operate the system, a laptop, something. We have customers that they have a truck, and in that truck they have computers, and the whole range of user interfaces should optimally be supported by us, and that's difficult. And there's a certain gap between C++ and nice cross-platform user interfaces. Of course, there are solutions, but it's not that easy. So, what are our requirements on this behalf? We believe that the user interface should run remotely, because there is no display on it, and we possibly couldn't manage that. It should run on multiple devices, as said before. We have some real-time-ish requirements. It's not that we need really real time in a bare metal sense, but a few tens to hundreds milliseconds should be something we want to have in our response rate of the system. And we have customers from the professional area, so it's not just that you have your remote control and have a tablet and can control the system through that. There's possibly another user sitting in a different room far away who also wants to manage and control the system. And so we have quite a bunch of requirements which cannot easily be resolved. And for that, I would like to go with you a little bit in the or look at possible options. What's the classical approach, and see what we have chosen for that to solve that problem. So the traditional approach, and I didn't write old or I didn't write bad approach. The traditional approach would have been, well, have some kind of display here and use a native interface. So basically you might have some application process, and in that application process you have your UI layer and you have the business logic, which is the drone control system in our system. So advantage, of course, it's kind of easy. It's the UI and logic share the same process. So you can efficiently implement that. At least the implementation is efficient. So the time you take as a programmer, and it has several drawbacks. It's physically restricted to directly connected user I/O devices and directly connected users, and we don't have them. There's only a limited amount of user libraries we can use for that, so it's not that easy. And that's a major point. UI and logic are not isolated. They are running not only on the same machine, they are even running in the same process, which means that certain bugs might affect the logic, even if only the GUI or the user interface would have been affected. So looking at the requirements, we currently don't fit quite well. The user interface doesn't run remotely, at least in particular not on several platforms. We have low latency, okay, but the user interface is not multi-user capable, so we are pretty much we pretty much don't have the solution now. So the next, let's say, extended traditional model is I have two processes, but still a physical, like a kiosk, a physical user interface at the device, and I add some kind of interaction layer to have a separate UI process, which lets me isolate my my user interface somewhat from the business logic, which is a good thing. I add some complexity, so the interaction layer needs to be you need to have technology for that. You need to do something, have pipes, have local host communication, whatever. You need to do something there. It's kind of an effort. It doesn't solve that you only have very little UI libraries available, and so it's still no solution. In fact, we haven't made anything better. We have made it more complex. Besides the isolation, the more modern approach might be to have a distributed system there, to have a separate UI device, to make use of a phone, to make use of whatever device is available of the desktop PC. And then you might have a UI process within the user interface. You have some interaction layer again, but this time it's going between devices. And you have the embedded device, which is somewhere else. We have to keep it like that for now. This has the big advantage that the UI process may use possibly also a different language, or at least an appropriate user interface for the target platform. UI and logic are not running on the same hardware, which is even more isolation compared to what we had before. So if now there's any crash in the user interface, it won't affect the backend at all. The drone won't crash. This is important. And the UI and logic, that's the drawbacks again, are not running on the same device. It's also a drawback. So there's effort that needs to be done for inter-device communication. And we have an additional component, which might be your cell phone, but it is an additional component. In theory, this approach would fulfill all our requirements. It's possible to let it run on iOS, Android, Windows, Mac OS, and Linux. It does support low latency for near real-time updates. Depends a little bit on communications technology and so on. And the user interface would be, in theory, multi-user capable. But if you, for example, implement for iOS, Android, Windows, Mac OS, and Linux a client, and you do this separately without any support from other libraries, you would get lost. You would never be able to fulfill that requirement with a reasonable amount of effort. So it seems a little bit that this approach must come at a high development cost. But there's good news. So we had an excellent lightning talk on Friday. We are standing on the shoulders of giants, and there's lots of technology that helps us to solve these issues and make it even not much more complicated than one of the scenarios I showed earlier. So the needed key technologies are already available and robustly available because they have been applied by, for example, the web community for, let's say, ages. So the multi-user problem has been tackled a long time ago with HTTP and WebSockets for bidirectional communication. C++ nowadays has some kind of stable WebSocket implementation, so we have somehow the bridge towards towards the web world, and we have good cross-platform serialization technologies, and this is also a needed building block in order to be able to implement this without too much effort. So let's get a little bit more specific now. When looking, so you see, I like block diagrams because you can very good understand from my perspective how an architecture or a stack is working. So let's have a look at the right side. There's the UI logic. Our proposal in this stack pattern I'm proposing today is to use HTML and JavaScript for that. You could use other stuff, but this is the proposal I'd like to make. Then there's an data or RPC layer, which is basically the interaction layer we had over there, which needs somehow to make the glue between some remote procedure calls we are doing and some data exchange we are doing. You need to do some data definitions and so on. Below that, there is a serialization layer, and I'd suggest to take protobuf for that because it's cross-platform. It has a broad support for many languages, including JavaScript and including C++. So it's a good choice again. But there's other choices. I'm not saying it's the best approach. It's just a very well working approach from our perspective. And now there's something interesting, because usually it's kind of difficult to interface something that is running in a browser, in an isolated environment, with something that is on an embedded device, because in the browser you cannot easily open just a TCP socket to do some communication. It simply doesn't work. So the browser community has said, okay, well, we don't want to have the possibility to open TCP sockets. It's some kind of security thing. But we might want to have something for bidirectional communication, and WebSockets are one of the options for that. There's also HTTP2 and some other new stuff, but let's keep it simple and stick to WebSockets for now. WebSockets are basically HTTP sessions that have been migrated towards a bidirectional data pipe, let's say it like that. So it's really HTTP is challenge and response, or request and response, and WebSockets allow for truly bidirectional communication. So each of the parties can initiate a communication. Okay, let's go on. Then there's a TCP IP stack, of course. Then we have the communication hardware, whatever that is. I will come to that a little bit later. We have, on the embedded side, we have again the TCP IP stack. We have the WebSockets, which can now be implemented, for example, by Boost ASIO and Boost Beast. So Boost ASIO is the underlying basic technology, and Boost Beast adds HTTP and WebSockets on top of it. And then we have the serialization layer with protobuf, and we can use the same data definitions here we created before. So we don't have to do anything probably except for running the protobuf compiler. And then we have the data RPC layer and the actual business logic. So in our case, the drone control system. So this is the proposed stack. And if we have a deeper look at it, it would even be possible without too much effort to let this approach degrade to a local setup where you have again some user interface directly on your device. So it's it isn't even more expensive than the other approach. It's simply more versatile. So let's revisit that. We said user interface must run remotely. Potentially on iOS, Android, and Windows, macOS, and Linux. And with web technology, we can do one implementation, not 5, and let it run on all these devices. It's a huge benefit in development effort that we can gain by using web technology. The only other option might be something like Qt. So Qt-ish solutions are, from my perspective, the only option to have similar effects there. We said when we're using web technology, plain TCP IP is out of scope. It doesn't work. There is HTTP2 and SSE. So this is basically some kind of a new way where servers can also initiate data transfer to clients. So this is HTTP2. And SSE is something to let this propagate into the user space. but this solution comes with a slightly higher protocol overhead than the WebSocket solution. Doesn't depend, isn't necessarily important, but yeah, in general that's the case. Well, if I have such an architecture, which is distributed, multi-user capability is kind of easy to implement. It's still some work, but it's kind of easy. So, why do we think that the UI with JavaScript and HTML is a good thing? For many applications, there is kind of good availability of frameworks in JavaScript. In particular, this is for UI relevant topics. For example, map layers. There is a huge amount of GIS libraries available there. Even 3D GIS data displays are available. So it's a good choice there. Browser debugging might be, in some cases, more convenient than native debugging on the embedded devices. Kind of a discussion topic maybe, and that's very important. The access to personnel is much better. So we are not limited to C++ programmers. We are not that many. So there's from a business perspective, it's much better to have the UI in a language that can be where you can easily recruit more people. And that's a bonus. The web application can be turned into something that looks almost like native by technologies like Electron or Ionic, or just using a kiosk mode of your browser. So there's really a lot of options to hide the fact that you're using web technology if you want to. Obviously, there are corner cases, or more or less corner cases, where where you need a native user interface. A native user interface is, for example, in the game industry very common, because when you develop a game and you really want to have the last frame per second out of your system, it's not a good idea to let that run in the browser. And there are other corner cases, in particular if you have certain specific libraries that you want to apply, when it's really necessary to work native. Well, this approach doesn't keep you from that. You can just pull out the JavaScript HTML part, maybe pull out the WebSocket part, and just use the protobufs you have defined earlier to communicate with your backend and use the same backend again for your system. In each of the scenarios where you had a separation between the process of the user interface and the embedded system and the business logic, you needed some kind of data definition for your interaction layer. So this is something you need to do anyways. So it's all, one could even say it's for free, because you have to do it anyways. For our actual implementation, I personally think that the RPC layer might be an optimization point. There are some RPC libraries out there which might help at some point to be faster in implementation and have less pain when switching platforms. The serialization layer consists of some kind of meta description of data that is converted to native code through a protobuf compiler. There are other alternatives to protobuf, of course, so it's just our choice, but I think it's a reasonable one. WebSockets, I said it earlier, start out as an ordinary HTTP request. So it's basically an HTTP session that gets migrated, and after the migration, the server may stream data, may send at any time, and the client can react on that at any time. It's a very thin protocol layer, and as soon as you have set it up, you can think of it as something like a TCP connection. It's not really one in the end, but there's some abstraction layer in between. But you have guaranteed in order delivery. It's stream based somehow, yeah, it's really something you can work on with well, idioms you already know from TCP/IP communication. And you need the WebSocket layer only for browser-based clients. Okay, the TCP/IP is the basis of the internet, so it's perfectly possible to make your device remotely available via the internet or via a company intranet. So if you have an embedded device and there is already a company VPN that connects two sites, your embedded device will be available for managing from the other side of the company, which is, again, in our use case, you can control the drone from anywhere in the world. So it's really a good thing. Yes, Beast is really a good solution for having the WebSockets in the C++ world, unless it has only been available for like 2 or 3 years in that quality. So it's kind of new. But it does solve this puzzle piece, and yeah, we can have now WebSockets in C++. What I left out all the time was the communication hardware. And communication hardware is a little bit oversimplified, because this is actually the glue that is necessary to make this setup work at all. And there is, to be honest, some kind of difficulty there. So if you are in a setup where Ethernet-based connection is available and possible for the user setup, so for the user, for the device that needs to control the embedded system, and for the embedded system itself, then you're all set. This works very well. If you need some kind of wireless or tethering connectivity, that's a little bit more difficult, because when you're using Wi-Fi, you have to look at whether your embedded device goes into a Wi-Fi network that is on the site where you deploy it, or it opens up its own access point, and then your mobile phone or whatever can only connect with your device and not with other devices at the same time, mostly. So this is somewhat, it needs some thinking for your specific use case. LTE, well, you usually don't have fixed addresses. You can have, but you usually don't. So your device is not available from the internet out of the box. You can solve that somehow with some VPN or whatever. So this is also a solution which needs some thinking. When you want to connect for this with some tablet or whatever through a cable, and you use some USB cable, you can make use of USB tethering, which is in most embedded or in most mobile devices available. It works but it's not so easy to make that work in all corner cases. So it's really a difficult thing. So in the end, I think this is the most complicated part to make that work for your actual scenario. But yeah, that's the job. Let me add some thoughts on our embedded environment. So on these devices we have Yocto-based images. The images are automatically built when we commit something and it has gone through a successful CI run-through. The proposed stack is cross-platform, so I can run the whole stack on my PC here, which I will show you later also. And we can also test the whole system, except of course for the hardware interfaces, in on one PC to make it possible to to develop efficiently. We use CMake, we use Conan in order to make it possible to achieve this cross-platform stuff, and yeah, mostly painlessly. I'd like to show you some stuff now. An example of the stack, like yeah, I have prepared. It's basically an extension of an example that has been part of Boost Beast. So Boost Beast provides a WebSocket multi-user example. It has some kind of yeah, in the main method. I'd like to show you first of all the fact that it's creating a shared state. The shared state is used by every module or every class in the program. It's very Boost ASIO-ishly, so it's sometimes one gets a headache about the shared pointers that are applied there, but yeah, it's in order to manage the life cycle fitting to Boost ASIO concepts. Here is a listener created. It's based, or it's attached to the I/O context, and it basically listens for incoming TCP connections, which are assumed to be HTTP connections, and possibly later on WebSocket connections. So we also have a timing-based ASIO handler here, which runs every 100 milliseconds, which does something like the business logic for this example, which it's some kind of basic example here. The overall program will provide a web interface using a web display of a map where you can see some entity moving. So this is basically what we are doing now. The WebSocket or the listener, basically, I'm just quickly going through that. It's a lot of Boost and Beast and ASIO magic, but basically it listens to the socket, and as soon as there is a socket coming in, it will get moved to an HTTP session object, so that the socket gets migrated to an HTTP session. The HTTP session serves for two things. On the one hand, it's an HTTP server which provides the HTML and JavaScript stuff and so on. And on the other hand, it provides the option to migrate the session to a WebSocket, so that we have the bidirectional data pipe I was talking about. So basically, when we have this web server, we have the possibility to access the web server here in the browser just by putting in the URL and the HTML file which I have created for the example. So, which is basically just this, and this is only a few lines of code to provide you with such a map display. If the browser connects to the user or to the embedded device, we can see here that the browser gets somehow some updates, and I'd like to show you how this works. So I said there is some kind of business logic there. So we have a tick handler which gets called every 100 milliseconds, and every 100 milliseconds it will actually move everything and send a status to the connected clients. And this is the streaming thing as I talked about earlier. This repetitive status sending is what we can do now, which would otherwise be very difficult if we hadn't the WebSockets. Yeah, so the move everything is basically, let's go, yeah, only some simple square moving. And the sending of the status is the instantiation of a protobuf message and sending it to, to the actual, or setting the current position into it, and then sending that to the web server, to the web client. So we can also have a small look at the web client, just to let you see how this works out. It's, as I said before, it's only one file with HTML and JavaScript in it. It has some kind of some code for the display of the map. It has some kind of some code for conversion of coordinates, and it has the protobuf library. And yeah, basically what the protobuf library does is it loads the data definition of the protobuf files we created before, and which look yeah, like this. Just there you have a status message, and it has some easting and some northing in it, and we have a server message at the moment only with one possible content, which is the status message. So you can basically just push server messages, put different contents into the server message, one of them being the status message, and that way you can push updates to the browser. Yeah, the client well actually is somehow more easy to understand than Boost ASIO. It just opens a WebSocket. I can, yeah, which is here. It opens a WebSocket, makes it binary, and registers a handler for data that he receives on that WebSockets. And we can now, yeah, push, when we receive that data, we can push that to the map display, and you can see here, yeah, actually how the movement takes place. In order to let you a little bit see how fast it is, I've implemented also the way in the other direction. So when I click on a beam home, it will move immediately towards the, well, our location. I have let it run too long, but I can do it now. You have seen it has reacted really responsive, so there wasn't any noticeable delay. It's almost immediate, and this is something that's not natural with web-based development. This is only an example. If anybody is interested, I can give it to you later on. What we have implemented with that is our user interface, and so basically you can see here a drone, and you can just send it around. You have even some kind of navigation system in there. So basically there's a lot of stuff you can do here, or not. So for example, you can plan a mission like in this area, and say you want to have like 20 meters between lines, and then he will plan lines for you for a flight path in order to cover the area. We can simulate the system completely here. I have running both the embedded side and the actual user interface side on my PC here, and the only difference is that we would just exchange some minor code snippet that interfaces with the actual drone and not run the simulator here. Okay, that's pretty much it for my talk. Thank you.